feel some factoring coming on. The denominator is going to be a little bit easier. X plus 3, x minus 3. Numerator, however, is difference of cubes. If you want to treat it as x cubed minus 3 cubed, you can. And that's going to give me x minus 3, and then x squared plus 3x plus 3 squared, which of course is 9. Again, difference of cubes. And we will cancel this with this. Because of that, we will have a hole in our graph. So we're going to keep going with this. We're going to have x plus 3 down here. Numerator is going to be this. It does not factor. Trust me, I've tried. X squared plus 3x plus 9. All right. X-intercept. Y-intercept. Holes. Oh, this is going to be fun. X-intercept, Y-intercept, holes, vertical asymptote, horizontal asymptote. Okay, let's start at the end on this one. Horizontal asymptote. All right, let's compare the degrees, and we can compare from the very beginning if you like. We would have x cubed and then x squared, so I have 0x cubed. That's going to give me 1 over 0. So the horizontal asymptote is 1 over 0. So there is no horizontal asymptote. Not going to happen. Okay, vertical asymptote is going to take place where the denominator is equal to 0. So x equals -3. Holes in the graph. Okay, that's where the thing that canceled, the factor that canceled, equals 0. So that's going to give me 3 comma something. I don't know where that is yet, but I'm about to find out. And we are going to type that in. Actually, let's not type it. 3 squared plus 3 times 3 plus 3 times 3. So that is 27. So there is a hole in the graph at 3 comma 27. That's way yonder up there. Okay, we're going to have to scale this thing differently. The y-intercept is at y equals 0 squared, 3 times 0 plus 9 over 0 plus 3. And that's going to give me 9 over 3, which is 3. Okay, I'd be tempted to go ahead and put a dot on 3, but I don't want to because I've got to go all the way up to 27 for something I can. Now the x-intercept is going to be a little bit tricky. Check it out. It's where your numerator equals 0. Because this does not factor, we run the risk of it not crossing the x-axis at all. All right, so we might want to get a visual for this one. You may want to graph this one in Desmos or on a calculator to see what it looks like, but trust me, because it doesn't factor, we run the risk of it not crossing the x-axis. We also run the risk of it being irrational, but I'll go ahead and tell you, this one, if you solve this using the quadratic formula, you would have complex solutions, also known as imaginary. Excuse me, sorry you had to hear that. All right, woo! So here's what I want to do. I'm going to graph just this and see where it equals 0. So let's see, x squared, yes, you can type it that way. And regular standard window, nope, not going to happen. So no x-intercept. No x-intercept. Okay, so not quite sure what to do here. Let's graph it. I do know what to do here, but I do want to graph it and give you a visual for it. So the original function was x cubed minus 27, and then x squared minus 9. Let's put your numerator and your denominator in parentheses if you're using a graphing calculator. Let's go to a standard window. All right, this one has a funky thing that we are not going to deal with in this class. That funky thing is the slant asymptote, okay? Which means that this line right here is a line that it will not cross. And I can find the equation of that line by using synthetic division on this fraction right here. All right, so I thought about scaling it differently. I'm not going to. 327, something about that feels wrong. Am I wrong? Let me double check. I might be wrong on something. Nope. Okay, it sure does give me an error when I plug in a 3. All right, I'm experimenting here. Hold on. Something about this feels very wrong. 3 times 3 plus 3 times 3 plus 3 times 3. But then when I look at the graph, at 3, it doesn't logically go through 27. Not that it would, because there's a hole there. All right, we're going to figure this out in real time in this video. If I plug in numbers that get very close to it, I should get close to 5.5. Oh, I know what I did wrong, silly, silly goose. I didn't divide by x plus 3, which would be 3 plus 3, which would be 6. Oh my goodness, and then the lights just went out too. Took forever to find that, my word. I'm sad by that. Yes, not 5.5, 4.5. There it is, 4.5, got it. Okay, I'm gonna keep this mistake in the video, and that way you'll realize that math teachers make mistakes too. I had an earlier conversation by myself about scaling this one differently because it was gonna go 3 to 27, and yeah. Don't forget to plug it into the entire thing. I plugged it into the numerator only. I was so busy looking at the numerator and its complicatedness that I failed to plug it into the whole thing. 3 and then 4.5. Excuse me. Y-intercept is 3. And we're going to graph this. And we're going to graph that. Okay, well we also, whoops, that's the wrong color. Making all kinds of mistakes. Been graphing all these in blue. Now we're going to graph the asymptotes in red. And we won't cross that line. Now, even though this is beyond the scope of this class, super fast, I want to show you what the slant asymptote really is going to look like, what it's going to be like. So, using the purple pen, let's divide. -3, and then 1, 3, 9. I briefly mentioned we can use synthetic division for this one. 1, -3, 0, and then 0, 9. My remainder is 9. So I'm going to be left with y equals 1x plus 0, and then a remainder. But this right here is my slant asymptote. Slant asymptote. Again, I'm just giving you a asymptote. I'm giving you a glimpse of what's to come in future classes. All right, so don't panic if you're like, oh, do we need to know that? No, you need to know that process, but you don't need to know that that's where a slant asymptote comes from. Not in this class, but I'm going to guide the general direction of this one with that. All right, let's do it. So, and then this one's going to be way down here, doing something like that. Okay, we're going to have two discontinuities, two x values where we have discontinuities, and one of them is going to be non-removable disco at x equals something, and then a removable disco at x equals something. Removable discontinuity is the whole, that's at 3. Non-removable is the vertical asymptote, that's at -3.